Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the casting. In this particular presentation, I will be talking about the failure of the steel casting, okay, failure analysis of the steel casting. But to understand the failure analysis of the steel casting and the related aspects, it is important to understand the way by which steel behaves during the casting and how the structure and properties get affected during the casting and which in turn affect the mechanical properties and the soundness of the casting. So, we will be starting this presentation with the content of the things like it will have the physical metallurgy of the steels, common issues in steel casting, structure and property relationship, and then one case study related with the failure of the high nickel casting, steel casting. Okay, and what the failure analysis procedure was adopted, the findings and observations, and the general strategy to avoid the failure. So, we know that let us understand about the little bit about the steel. So, the broadly we have two broad categories of the steels. One is the carbon steel and another is the alloy steel. So, carbon steel is about the plain carbon steel, okay, where the other than carbon, manganese and silicon, these are the elements which are maintained in the certain range, while the sulfur and phosphorus are maintained the level below the 0.05%. So, if the concentration of these elements is more, then they will be very adversely affecting the performance of the casting, making them brittle or very sensitive for the hot cracking. On the other hand, the manganese and silicon content is also kept within the certain band, which may be like say the 0.8 or so. Okay. But the carbon content is controlled very closely in order to have the controlled structure and properties. So, other elements like manganese, silicon, sulfur and phosphorus, these can be termed as residual elements. Okay. These are not expected to affect the properties of the casting to a great extent. So, if the carbon content is the main parameter as far as the steel plain carbon steel composition is concerned, which is affecting the structure and properties. So, it is important to learn about that. There are three broad categories of the plain carbon steel. So, you can say a low carbon steel having the carbon content less than 0.5%, medium carbon steel having the carbon content in the band of 0.25 to say 0.5%, and the high carbon steel, okay, medium and high carbon steel. So, high carbon steels will have the carbon content greater than 0.5, but there is a limit. Theoretically, this limit is around 2%, but we usually do not have the steels greater than 1%. So, carbon content in high carbon steels is usually 0.5 to 1%, but theoretically it can be as high as that of the 2%. Okay. On the other hand, when the only carbon content in the carbon steel is increased, what we notice is that increasing hardness. So, the carbon content is say increased say from 0.1 to 1% say for example. So, hardness will be continuously increasing. Tensile strength also increases up to the 0.8% of the carbon. But at the cost of these things will be happening at the cost of percentage elongation, that is ductility and the toughness. So, these are compromised very badly, okay. And this is happening due to the changing proportion of the ferrite, alpha, iron and the pearlite, which is a mixture of the ferrite and cementite. Okay. So, continuously increasing carbon content decreases the proportion of the ferrite and increases the proportion or the relative amount of the pearlite, and that is held responsible for increasing hardness and strength and reduction in elongation and ductility. If we see, so this is the typical thing, like we get the higher strength and hardness, but at the cost of the elongation and ductility. So, this may not be very favorable situation, because most of the time we want very good combination of the strength and the toughness. So, how to achieve that? So, what has been done, which is not possible said is so easily in with the carbon steels, because increasing the carbon will increase the strength and hardness, but at the cost of ductility and toughness. So, what has been done, like the controlled alloying of the steel or carbon steel or plain carbon steel helps to like say refine, increase the refinement, grain refinement say, or forming the formation of certain favorable constituents, favorable phases in such a way that you get the higher strength without much compromising the toughness and ductility. So, that is the benefit which is achieved through the controlled alloying. Okay. So, controlled alloying may be done through the number of elements like aluminum, chromium, nickel, vanadium, titanium, tungsten, etc. There are wide range of the alloying elements which can be done, alloying elements which can be added in carbon steel to enhance the certain specific kind of properties. So, these properties may be in terms of high corrosion resistance, okay, high temperature properties, higher strength without compromising the ductility and toughness, like that. So, depending upon the amount of the alloying elements which are being added, if it is a alloying element added is less than 1%, then we call it as a low alloying elements. Then medium alloy steels, low alloy steels when the alloying content is less than 1%, and if it is like say 1 to 10%, then medium alloy steels, and high alloy steels alloying content is greater than 10%. So, one of the most common kind of the high alloy steel is the stainless steel. So, stainless steels they usually have chromium greater than 12% in order to have the stainless effect on the steel. And there are three variants of the stainless steels like ferritic stainless steel, martensitic stainless steel, austenitic stainless steel, and precipitation hardenable stainless steel. And similarly, there is one high nickel steel is also used for various engineering applications, especially for the high temperature applications. So, where good strength even at a high temperature is needed, then high nickel steel is preferred. So, let us see like how the different with the variation in carbon content, how as a function of temperature, how the different phases are being formed, and that is what we can easily study with the help of this phase diagram. So, what happens, let us see this the diagram which is in the right side. What we can see, the steel in the say iron in the molten condition, as soon as the temperature starts coming down at around 1540 degrees centigrade, solidification starts in case of pure iron. Then initially it forms the delta iron, okay, delta ferrite, and then again the delta ferrite will convert into the austenite, and then austenite will convert into the alpha ferrite. Okay. This is how the changes will be occurring, and there are three stages. One is where liquid to solid state phase transformation occurs at 1540 degrees centigrade, then at 900, then at 1395 the delta ferrite will be transforming into the gamma, okay, that is the austenite, and then gamma will be transforming into the alpha, that is the alpha ferrite. Austenite will be transforming into the alpha, okay. So, that will be maintained till the room temperature. That is what will be happening in case of the pure iron, okay. But what if the carbon content is added in the steel? So, that is what we can see. What if the carbon is added in the iron, okay. So, that is what we can see here from the iron carbon diagram. What it shows, the carbon content is increased say from 0 to 6.6 percent of the carbon in the x axis, and y axis shows the temperature. So, if we see the point L shows the composition or the carbon content corresponding to the eutectoid point, okay. This is the solid state, this will be occurring at the solid state. So, at eutectoid point at the point L, the gamma transforms into the perlite, okay. So, that is a mixture of alpha iron and Fe3C, mixture of ferrite and the cementite is formed. But if the carbon content in steel is less, so let us understand first the range of the carbon content theoretically in the steel, say here up to this is the range, this is the range of the carbon for the carbon steel theoretical range, but usually we do not have the carbon content greater than 1%. Okay. So, let us say when the carbon content is steel less than corresponding to the eutectoid point, then what we call hypoeutectoid steel, when the carbon content is less than 0.8, that is corresponding to the eutectoid point. When the carbon content is greater than 0.8 or corresponding to the eutectoid point, then will be, so that is this one on the left side of this eutectoid point. So, that in that case the steel will be termed as hypereutectoid steel. Okay. So, at the eutectoid, the steel corresponding to the eutectoid composition will be simply termed as eutectoid steel, means indicating the carbon content is 0.8%. So, what it has at 0.8% means whole of the austenite will be transforming into the perlite only. Below that, for hypoeutectoid steel, on cooling from the molten point followed by the austenitic state, then it will be austenite will be transforming into the alpha ferrite as a pro-eutectoid phase followed by the perlite transformation. So, pro-eutectoid phase alpha ferrite is formed and then perlite is formed in case of the hypoeutectoid steel. But if it is the hypereutectoid steel, initially Fe3C will be formed followed by the perlite formation. So, this is the difference. Pro-eutectoid phase in case of the hypereutectoid steel is Fe3C, while in case of the hypoeutectoid steel it is alpha Fe, okay, alpha ferrite. Okay. So, this is what, in addition to the different phase formations, what it shows that on cooling what will the phase, what are the different phases that will be formed for a steel of given composition, or on heating what will be the order in which the different phases will be formed on heating from room temperature to the melting point. So, this is what we can see from the iron carbon diagram. Okay. So, mostly if we talk of the steels means the carbon content is usually less than 1%. So, either will have the 100% perlite or little bit cementite and perlite in case of the hypereutectoid steel, or mostly ferrite plus perlite in case of the hypoeutectoid steel. So, this is the thing which will be happening. So, the ferrite, alpha and perlite, these are the stable phases at room temperature. Similarly, Fe3C cementite and perlite are the stable phases for hypereutectoid steel at the room temperature. Okay. So, these are the stable phases. So, when you heat these steels, what will be happening up to the, say initially there will be a recrystallization of the iron, thereafter the perlite will transform into the austenite and then ferrite will transform into the austenite and will be having the 100% austenitic state. The same thing will be happening in case of the hypereutectoid steel, where perlite will be transforming first into the austenite followed by transformation of Fe3C into the austenite, and then we will be getting the homogeneous austenitic state. This is important especially to study what happens when the steel is heated or when it is cooled. But this is about the phase transformations which will be happening under the equilibrium conditions, but most of the time during the manufacturing, like whether it is casting, welding or machining, we do not come across the equilibrium condition, but the different cooling rates are used. So, we have to see like how does the cooling rate being imposed during these manufacturing processes will be affecting the end phases and so the properties of the casting. Okay. So, this is just a schematic way to represent what happens to the steel when the carbon content is increased. Say plain carbon, in carbon steel carbon content is increased, what happens? The ferrite is decreasing and perlite proportion is increasing, and after reaching at the eutectoid point there is a 100% perlite. Okay. And thereafter for the carbon content greater than 0.8 corresponding to the eutectoid composition, the cementite starts appearing as individual phase, and this because the ferrite is soft and ductile, okay, while this is little hard and strong. So, this reflects in the variation in properties also. So, what happens when the ferrite is decreasing and perlite is increasing, that is what we can see, the strength and hardness hardness increases continuously, strength increases up to the eutectoid point, and thereafter starts decreasing due to the formation of this weak cementite phase. And but the formation of the hard and a strong phases means the reduction in ductility and toughness. That is what we can see. So, say when the carbon content is very less, say it is almost nil, so you have ferrite only. Okay. When the carbon content is little more, the you have mostly ferrite, but with little bit amount of the perlite here and there. So, this is the case when you have further higher carbon content, you have perlite, lot of perlite, but ferrite at the grain boundaries, and then for corresponding to the point you take 0.8% carbon, you will have 100% perlite, and if it is say 1% which is corresponding to the hyper-eutectoid steel composition, at the grain boundary will have cementite, then perlite in the matrix. Okay. So, this is what suggests like when the carbon content is increased from 0 to 1, how the relative amount of the various phases, how the phases will appear and their relative amount will change in the microstructure, and that in turn will be affecting the mechanical properties of the casting, okay, of the steel. So, this is what is there, say this is particularly true for say 0.6% carbon steel, where the ferrite is there a little bit at the grain boundary and mostly the matrix is composed of the perlite. And so, here corresponding to that, if we see the ferrite percentage is less, so mostly your the ferrite is less, and the mostly it is predominated by the perlite concentration. So, this will be reasonably good in terms of the strength and ductility, but little lower in terms of the so this the steel corresponding to this 0.6% carbon steel will be strong and hard, but little bit lower in terms of the ductility and toughness. So, steels I have said the carbon steels will primarily be having the carbon content, but if we are talking about the alloy steels where the alloying elements, variety of alloying elements are added, then they affect the number of things. Say they affect the strength, they affect the eutectoid, the carbon content requirement for the eutectoid transformation, and it also affects the temperature at which eutectoid transformation will be occurring. Okay. So, if we see this trend increasing the amount of the alloying elements, variety of alloying elements, nickel, chromium, manganese, silicon, molybdenum, tungsten, all these increase the carbon content required for eutectoid transformation. Means in the presence of alloying elements, the eutectoid transformation will be occurring even with the lesser percentage of the carbon content. Okay. On the other hand, if we add certain alloying elements like titanium, molybdenum, silicon, tungsten, chromium, then these will be increasing the eutectoid transformation temperature. In carbon steel, it may be like 727 or 730 degrees centigrade, but in presence of the alloying elements, it will be going higher, means it will be making the ferrite stable. On the other hand, the manganese and the nickel, they will be lowering down the eutectoid transformation temperature, means they will be making the austenite more stable and reducing the stability of ferrite. Okay. Now, if we see the effect of alloying elements, the alloying elements in addition in the iron affects the things in multiple ways. For example, it may form solid solution, which may be of a substitutional type or interstitial type solid solution. It may lead to the grain refinement, it may lead to the formation of the unique phases and the intermetallic compound formation. So, there are multiple ways by which these alloying elements can contribute towards the strength. So, if we see this then addition of the carbon, nitrogen and phosphorus is very effective in increasing the yield strength, because what we see here, increasing the little addition of these alloying elements increases the yield strength significantly, while the effect of silicon, copper, molybdenum, manganese and the chromium is somewhat less effective as compared to that of the carbon, nitrogen and the phosphorus. Carbon, nitrogen, these will be forming interstitial types of solid solution, and thereby they will be increasing the yield strength significantly. The chromium addition here we can see decreases the yield strength initially. So, here now as I have said, The phases that we see in the iron carbon diagram, they are corresponding to the equilibrium conditions of heating and cooling. What happens when the carbon steel is subjected to the heating and cooling under the equilibrium conditions. But we hardly come across these kind of situations in real manufacturing scenario. The cooling rates are high, heating rates are high. Okay. So, what we need to see here is what happens, say steel is in the complete homogeneous austenitic state, and what if the steel is cooled slowly. That is what this is, the continuous cooling transformation diagram, temperature in y axis and the time in x axis, which is in the log scale, and linear scale in the y axis. So, what happens when the steel is cooled slowly? What we get? Austenite transforms into the coarse perlite. Okay. Initially it transforms into the austenite plus perlite, there is a two phase zone, and then fine perlite. Then if we offer little higher cooling rate, then it will be leading to the fine perlite. Okay. Then furthermore, higher cooling rate if used, then part of the austenite will be transforming into the perlite, then then remaining austenite will be transforming into the martensite. Okay. And if the cooling rate is further higher beyond the critical cooling rate, say corresponding to CR4, then whole of the austenite will be transforming into the martensite. And if further higher cooling rates are used, then of course, the whole of the austenite is going to transform into the perlite. So, this is important, especially considering the variety of cooling conditions which are experienced during the manufacturing. Say if even during the casting, if we use the sand mold casting, cooling rate is very low, which that can lead to the development of the coarse perlite, and in case of the die casting, the cooling rates are high, and so it will be leading to the formation of the fine perlite. Or if the cooling rates are further high, section thickness is very less, then even it can form the martensite kind of the thing. So, depending upon the cooling conditions being experienced by the molten metal during the solidification, the variety of the phases will be formed. Okay. So, say the case study is so this the high alloy steel category. If we see the stainless steel, which usually have the chromium content greater than 12%. Okay. Stainless steels are composed of multiple alloying elements. So, the common alloying elements in the stainless steel are like say the nickel, chromium, okay, carbon, nitrogen, molybdenum, manganese, silicon, niobium and titanium. So, in amongst these elements, some of the elements, few elements are austenite stabilizer, and few are ferrite stabilizer. So, the ferrite stabilizers, their combined effect on the ferrite stabilization is seen in terms of the chromium equivalent. So, effect of all alloying elements towards the ferrite stabilization is seen in terms of the chromium equivalent. Okay. While the effect of all alloying elements towards the austenite stabilization is seen in terms of the nickel equivalent. So, the nickel equivalent and chromium equivalent, say take any steel, try to see what is the composition with the weight percentage of the different alloying elements, and then calculate the corresponding nickel equivalent or chromium equivalent. If you want to calculate the nickel equivalent, then consider the weight percentage of the nickel, weight percentage of carbon and nitrogen and manganese, and use this equation. What it says, weight percent of nickel directly added, and then 30 multiplied by carbon plus nitrogen, 0.5 multiplied by the manganese content, and algebraic sum of all these will be giving us the nickel equivalent. Likewise, the chromium equivalent is also calculated, where chromium content directly added, then molybdenum content is modified with multiplied with 1.4%, silicon is modified with 1.5%, niobium weight percent is multiplied with 0.5, and then titanium is multiplied with the 2. Okay. Titanium weight percentage is multiplied with the 2 in order to obtain the chromium equivalent. Once we have obtained for a given steel, we have got a value of the chromium and nickel equivalent. Say the nickel equivalent, say for some steel is 11 and chromium equivalent is 18. Okay. So, these chromium and nickel equivalent, these 2 points will be used, these 2 values will be used to locate a point in this diagram. So, in y axis, this is a Schaeffler diagram, which shows the effect of nickel equivalent and chromium equivalent on the formation of the various phases in stainless steel which can be there. So, it shows the multiple zones, say martensite plus austenite, austenite only, austenite plus ferrite, and ferrite, austenite, ferrite and martensite. Okay. And the one hard and brittle phase like sigma phase is also formed in case of the high austenitic and high chromium stainless steels basically. Okay. So, if we see say nickel equivalent is 11, say somewhere here, okay, and chromium equivalent is 18, okay, somewhere here. There is a possibility that the steel will have all austenite plus martensite plus ferrite, but if the situation is a little different, say the nickel equivalent is 21, then the things will change significantly. Nickel equivalent is 21 means it will be the 100% austenitic stainless steels. My point here is we can estimate the phases which will be there in a stainless steel considering the composition using this kind of the phase diagram. Okay. And here 100% ferrite at this boundary and 100% austenite at this boundary, and in between the increasing proportion of these phases. So, increasing proportion of the austenite this side and increasing proportion of the ferrite on this side. So, depending upon that, it is possible like along some line there is a 50% ferrite and 50% austenite. That is also one of the possibilities. Okay. So, now we will see like the cause and effect diagram is one of the most common diagram which is used to see like what are the various factors that can be responsible for occurring the failure, and the factors which can be considered to analyze the various aspects, like it can be manpower, machines, methods, measurement, material and the environment, and there are multiple smaller factors related with each one which need to be analyzed to see which factor can contribute towards the particular failure. Let us see, this is one example where what we can see here, the failure analysis of the high nickel steel of the U clamp. The high nickel is the U clamp made of the high nickel steel. Okay. So, say this is the U clamp which was used for holding the tubes and pipes in case of the petrochemical industry. So, this steel was made of say HK 40, this component was made of the HK 40 steel having 25% chromium and 20 nickel, a common, which is a common cast steel used for the high temperature applications. So, in this case it was used for making the U clamp for holding the tubes U clamp, but this U clamp failed prematurely during the installation, and therefore, it was subjected to the failure analysis, and it was found that the gaseous porosity and shrinkage porosity were the main reasons behind the failure as confirmed by the X-ray analysis and the NDT using the X-ray and the metallographic studies, and presence of these cavities and porosities resulted in the significant reduction in the ductility and the toughness, and therefore, the U clamp in failed in the two cases, one which was next to the weld joint where which was providing the support to the U clamp, and another section where from the U clamp failed was from the bend section. Okay. So, the U clamp was analyzed for the composition, and it was found that the carbon content is 0.38 with the main elements, the chromium is 24.79 and nickel is say 19.65. These were the main allying elements, and based on this efforts were made to also characterize the composition of so after this compositional analysis, efforts were made to see how about the mechanical properties of the steel which has failed, of the component which has failed. So, the yield strength, 3 samples were tested, say 3, and the yield strength was 300, 287 and 284, and ultimate strength was like 389, 444, 441 and 371. Elongation was 4, 7, 10 and 4. And there is one sample which was failed prematurely while fitting, it did not show any kind of the strength. As per the requirement, the yield strength should have been like say the 240, tensile strength should have been 425, and the ductility should have been 10. So, in some cases it was observed like ductility was reduced, strength was also little lesser, and the yield strength was also was on the higher side, which indicates that it tends to behave like a brittle material, because the clamp failed suddenly, which was very surprising during the installation. So, these were the locations, the type 1 failure, where the one location the U clamp failed from the near the weld joint, where it was getting support from the foundation, and another failure occurred from the bent location. So, this also occurred due to the presence of the pores, uh, and which resulted in the loss of ductility. And when these sections were analyzed, what was found, like there was a lot of porosity. Okay. So, this section resulted in lot of porosity, big the pores were found, and if you see this, the morphology of these pores, these are the shrinkage pores, okay, as evident from the presence of the defect, okay, and the large air pockets were also observed in the bent section. So, the presence of the pore was the main reason behind the failure of the U clamp. Okay. So, how this kind of thing happen, like when the solidification is taking place, there will be dendrite formation on the both the sides, but when the dendritic arm start obstructing the path of flow of fluid, then these the spaces between the interdendritic arm is not filled in, and that in turn leads to the formation of this shrinkage porosity, okay, in the casting. So, efforts have been made by multiple researchers to find out like what can be done, what are the conditions which are promoting to this kind of the porosity. So, Niyama and ETL proposed that local solidification temperature, solidification parameter, which they termed as a Niyama value Ny, and so what they suggested, like there has to be a particular value of a parameter Ny, which they termed as a Niyama value, which is the ratio of the G by square root of R. G is the temperature gradient and R is the cooling rate. So, they calculated basically the Ny parameter to see what is the possibility of the shrinkage porosity formation during the casting. Lower Niyama value increases the shrinkage porosity tendency, and the increase so it ensure the minimum Niyama value for suppressing the formation of the micro and macro shrinkage porosity. There is a critical value which is helpful to avoid such kind of the porosities. In case of the micro porosity, critical value for the micro porosity is higher than that for the macro porosity. Okay. Minimum Niyama criteria value for producing the radiographic quality, radiographic sound casting in the high nickel steel was around 1 square root of K square root of second and divided by mm, okay, which is much higher than that for the carbon steel. It is just 0.8, say carbon steel 1025 carbon steel. So, the value is much higher for the high nickel steel than the carbon steel uh, for avoiding the porosity. So, as far as the report is concerned, the failure was primarily caused by the porosity, micro and shrinkage porosity, which reduced the ductility and toughness of the strings. So, remedy, it was as a remedy, it was suggested that do the proper melt treatment and reduce porosity, design the gating system properly, so that the proper thermal gradient and this kind of porosity is avoided, so that proper temperature gradient is maintained during the solidification, and follow proper mold design and cooling rate to avoid the micro and shrinkage porosity. That is all. Thank you for your attention.